Cheers, Jed. As most people have said, thank you very much for having me. I love Berlin. Every time I come here, I think about why I haven't been here in so long, and maybe I should just even move here. It's that great. So thanks. So as Jed said, I'm Patrick Hamann. You can catch me at Twitter, at Patrick Hamann, and I'm here to talk to you today about CSS and the critical path. Now, what does that actually mean? And is it even related to CSS? We're at CSSconf. So hopefully all will be explained over the next 30 minutes. So if you haven't guessed already, I work for The Guardian, a UK liberal newspaper, but we're now an international media organisation with 3 editions, 3 offices across the world. And over the last 18 months, I've been a senior engineer on the Next Generation project, where we've been building the next generation of The Guardian website completely from scratch. A new responsive website that currently we're delivering to mobile devices and hopefully coming to a desktop near you very soon. And as Brad Frost once coined the phrase of, we're using a technique that we like to call planting the responsive seed. So other large organizations like the BBC and ourselves, you know, when you turn around to your stakeholders and you say, right, we're going to completely chuck away the whole entire code base and rewrite it from scratch. How are you okay with that? And, you know, it's very daunting for them. So we actually used our m.dot subdomain as a testing bed for this, you know, new mobile-first and responsive techniques. And then last year we moved that over to the www domain. We kind of did a bit of UA sniffing, and we're serving all devices up to around 7 inches. And then, as I said, hopefully this autumn we're going to turn off the entire old platform and be serving all devices on the new platform. So today I'm here to talk to you about some of the lessons we've learned on being able to make this site load as fast as possible, and how your CSS is completely intertwined with that. In March of this year, we broke a new record at The Guardian where we had 100 million users, and last month we broke that even more with 105 million. And I'm very proud of the company and the team and how this is just an onward going trend. But the current platform that The Guardian that you know and love was not designed to cater for this amount of people. And more importantly, we now see over 6,000 to 7,000 uniquely different devices accessing the platform every single month. Again, the platform was just not designed to cater for this. All these different screen sizes, browsers, features, you know, it's just a combination that we just couldn't have imagined 10 years ago. Our platform wasn't designed for it. We needed a better solution. And more importantly, the old system has become a monolith over the years, features bolted on top of it. And we knew this, and our customers were telling us this. The platform was slow, incredibly slow. And so here's an example. On the right-hand side is the new site. On the left-hand side is the old site. And this is actually how a user perceives the loading of our page. And so you see in under a second the new page renders, and it finishes in 5. It used to be 3, but then adverts come along and ruin everything. And the old site is still crunching along. The median average for the old site to load is 12 seconds. That is not acceptable. But it's not just The Guardian's problem. This was taken literally this morning. I ran a query using the httparchive.org data on Google BigQuery and asked it, what is the average speed index of our websites today? It's taken from the top 10,000 Alexa websites. And this is shocking, that the median average, lasers, is the 90th percentile is way over 15 seconds. And the average medium is 9 seconds. It's not just our problem. This is collectively a problem of every single web developer in this room. The web is slowing down, and we need to do something about it. And we know now from studies that users also want their web pages to load fast. In the year 2000, the average user expected your web page to load within 12 seconds. Now, in 2013, they expect it to load under 2. And so, like any of you would do when you go out and build a new product, we went and surveyed our users and asked them about 17 of our key product drivers. And they rated speed as the second most important factor to their product, only after easy-to-find content. And you would hope that on a news website, the content was easy to find. So our users really, really do care. And this was actually unsurprising to me that they rated speed so importantly, but it came as quite a surprise to our stakeholders. But the great thing for me is that then that allowed me to use it as a leverage so we could invest in speed when we were building this new product. And Nicole did a great job at talking about Jacob Nielsen's research around this and about actual user perception. So this is research, HCI research taken from Ilya Gogorik's very amazing book called High Performance Browser Networking, which I strongly advise you all to go and read. But again, Nicole's already covered this, but for a user to feel like a machine is working, you need to get a response within 1,000 milliseconds. And after 10 seconds, after 1 second, there's a mental context switch, but after 10 seconds, the task is abandoned. So this might not just be, we don't just have to relate this to websites. I could be sitting at home on my sofa, changing the channel on TV. I need that machine to respond to my input within 1,000 milliseconds, or else I'll have a context switch. Again, so you're searching on the internet, you click a link, you need that website to render within 1,000 milliseconds. And so that's what I'm here to talk to you about today. No longer, as web developers, can we be thinking in seconds. We have to be thinking in milliseconds. And we started to think at The Guardian, and like a lot of other people have done, Tim Cadleck's been a good proponent of this recently, of what if we were to set ourselves a budget for every new feature that we built in this website. We had to enforce that every page must render within 1,000 milliseconds. How can you start baking this into your development workflow, setting ourselves a rendering budget? And that's exactly what we did. But I need to take a step back now. We need to actually, for us to be able to do that, we now have to have an understanding how browsers actually go about painting to the screen. What is the path in which they take from you clicking on that link to painting on the screen? So we need to go and actually understand a bit about the browser internals. And I strongly believe that us as web developers knowing how browsers internally work help us make better decisions in every day that we go about engineering. So that starts with, obviously, a network request. Hopefully, you've all seen one of these before. It's a segment taken from a waterfall in web page test. We had the DNS lookup that's transforming that lovely human-readable domain string into an IP address. We then have to do the TCP connection, a three-way handshake, incurring maybe multiple round trips there. Once we've got that socket connection, we can then actually perform the HTTP request, like get, I want to get that index file. And then eventually, that's our turn to byte, and eventually we can then download the content. And so all of this, if we start to think about this in relation to our budget, this is taken from a great resource on Google PageSpeed's Insights. On a UK average 3G connection, I presume it's probably definitely the same here in Germany, 600 milliseconds of your budget is already taken up by latency. Latency is the biggest killer to performance. And so I have no control over that. And on a 2G connection, it's probably even more. It's in seconds, and our budget's just gone. So that only leaves us with 400 milliseconds to play with, really. So again, let's have a dive deep further. This is quite a simplistic overview of the path at which most browsers will take. They all differ slightly, but most of them generic, it can be boiled down to this, of the path that they have to take from clicking on a link to painting to your screen. So we've already seen what the networking is there, incurring the 600 milliseconds. We finally have a HTML file. Now, one of the beautiful things about HTML is that it can be parsed incrementally, and we can build the DOM incrementally as we parse the file and as the bytes come in. And so we're parsing that, we're building a DOM-like structure, but we have to stop. As soon as the browser finds a script element or a link element linking to your style sheet, it has to block render. It cannot carry on with parsing and executing the DOM. It has to stop. Go back and perform that networking again, incurring that 600 millisecond barrier. So we've already, just by having our HTML and CSS, have already blasted through our budget. Once we have the CSS file, and once we have all of it, it's very important to stress here that browsers can't do partial parsing or rendering of CSS because of the nature of the cascade. If it started rendering stuff that it found here, styles later on in the cascade might overwrite them, and you get this horrible mess of reflowing. And so, quite rightly, the specification says we have to have the full file before we can parse and execute it. So once we've got that, we can create what's the often forgotten CSS object model. And so it's just like the DOM, it's a tree-like structure, but containing all of the style node informations relating to nodes in the DOM. But we've forgotten someone, our lovely friend and foe, JavaScript. He is tightly intertwined and tightly coupled with these two object models, these two trees, the DOM and the CSS object model. DOM construction cannot proceed until JavaScript, one, has been parsed, but most importantly, has been executed. Because, unfortunately, there are great features of JavaScript that we know and all love, like document.write. JavaScript can manipulate the DOM, it can ask the DOM, it can change the DOM. But there's another tight coupling here, that JavaScript cannot execute until the CSS object model is available. Obviously, because if JavaScript queries the DOM for a style on one of those nodes, we have to have that information. So JavaScript blocks rendering of the DOM. It blocks DOM construction, but it has to wait until CSS is ready. So it's this horrible intertwining. And that is why we have the age-old best practice of your JavaScript at the bottom and declaring it asynchronous or deferring it, making a promise with the browser that it's not going to alter anything. It's not. You can perform the networking for this whenever you want. I don't care. It's not critical to my rendering. And that's trying to beginning stressing the point here. CSS really is the only thing. Once you've declared JavaScript as asynchronous, CSS should be the only critical thing to painting to the screen. And once we have that information, the browser can construct a render tree. And now a render tree, again, is another tree-like structure containing all the information from top left to top right to down. But it will only contain the information required to paint to the screen. So if the CSS object model says that a div is display none, that div will not make its way into the render tree. It's only the information that we need. Once we've got the render tree, the browser can then perform layouts, i.e. calculating the geometry of every element and its positioning on the page. And this is where you might well have known and seen in your favorite developer tools that you'll see we've now got timing information for layout, or also known as reflow after the page. And so every amendment to the DOM you make, you're causing the browser to reflow. You're causing it to recalculate all the geometrics on the page. And finally, we can then paint to the screen. And so let's have a look at this in a different way and seeing actually how this path is constructed. As we're saying, we're requesting a page, and this is our render process on the top. We get the HTML file, we get the response, and all the time we're blocking rendering. This is just idle, that process, blocking rendering, incurring the networking again. We've declared our JavaScript as asynchronous, so actually that can be run afterwards. Finally, we can render the page here. And this is your critical rendering path. CSS is the only thing that should be on it. And so we have a look at that again back at our waterfall. Because we've declared the JavaScript as asynchronous, we're waiting for the CSS to block, and eventually here's our start render event. We must get the CSS down as soon as possible. In my opinion, it is the critical path. So hopefully you might begin to start to think where I'm going here with this. How can we optimize CSS for this critical rendering path? But then when you start to think about a responsive website, what actually is your critical CSS? What is your CSS? The minimum amount of CSS that you need to render your core content, the content that your user came here for. But unfortunately, in a responsive world, that concept of above the fold is a very tricky thing. It's a hard problem. And so what is your critical CSS? Is it your sharing widget? Is it the popular content module? Is it your comments or your related content, or definitely not your commercial components? No. None of this is critical to the page. It's not what the user came here for. My users came to read the news. And therefore, the only CSS that should really block my rendering is the article itself and maybe the navigation at the top as well. That is the only critical CSS on my page. And so we've taken this notion quite far at The Guardian, that in fact we have a rule that we don't even allow any of those components to block rendering. So we actually send only in the initial payload, the only HTML that gets sent down to the document is the article itself, and then we progressively enhance the page via JavaScript and loading in the CSS for that later. And so what we're left here with is very streamlined, critical content. So what if we were to inline that critical CSS into the top of our document? the browser wouldn't have to perform that 600 milliseconds overhead again. It will have all of the information it needs within one single HTTP request, and so it could instantly paint your critical content. So that's exactly what we started to do at The Guardian. But it goes against everything that we have been taught as front-end developers. Separation of concerns, your CSS, your styles in your style sheets, your behavior in your JavaScript. You know, HTML shouldn't really have, like the pure nature of the text, shouldn't have presentational data inside it. It's just for machines to read. It goes against everything. And the first time I saw this, I was like, what the fuck are we doing? But actually, you'll see in a second why it's so important. So if you go to our beta site now, and you literally inspect the source, you'll find a dirty, great block of CSS right at the top of our page. And now it's important to note here, something that I didn't mention earlier on in the networking, is that obviously it could be detrimental if you were to put the entire styles in your document. In fact, you'd cause your content download to be longer than the initial paint. And it's also got caching issues with it as well. So we have to limit this block of information to 14 kilobytes. And the reason why that is, if some of you know about TCP, TCP has a great feature called slow start, and it means that the initial congestion window for a TCP socket has to start off small. And that can, if your server's set up correctly, the congestion window will be 10. So it's 10, the first 10 packets. And the first 10 packets equates normally to around 14 to 16K. So if you want to get all of the information required to render your style sheets in the first round trip, so not incurring any more latency, you have to limit that to 14K. You can start to see how tricky this starts to get. You know, your critical CSS needs to be within 14 kilobytes. Nothing else can block that. But then, it's magic. Your browser has all the information it needs. And so, again, how does our users actually perceive this? So on the top here, we've got our website loading without inline CSS, and the bottom with. I apologize for the person's face in this. Oh, man, that's a British joke. Yeah, sorry. What you'll see here, though, is that with inline CSS, we rendered way within our budget, 600 milliseconds. And then afterwards, you know, we're miles ahead. We've nearly finished rendering the entire page, and that one hasn't even started. But the observant people in the room would have noticed, well, you know, you've only got 14K of CSS here. Where's the rest of it coming in? And it's because CSS is a blocking resource, we have to hide it from the browser. And essentially, by doing that, we have to load it asynchronous. So at the bottom of the page, we've got a JavaScript function that if we deem the browser to be a modern browser, then we load it with an AJAX request. If the response from that was 200, and then we can inline it in the document and maybe cache it, which we'll talk about in a bit. And if it's not, we'll just load it with a traditional link tag and be done with it. So you'll notice there that I mentioned the caching of this, because, again, the more observant in the room, hang on a second, you know, you're loading it asynchronously. Your browser's already painted, but surely you're going to cause another massive reflow when the new stuff comes in. And actually, again, that's going to be detrimental to your users. And when we first started using this technique, we didn't do any form of caching. And with every paint, we got this, yes, it loaded and it rendered fast. And I was like, look how fast our site loads. But then the creative director of The Guardian came in to my office and was like, what is this double flash on my website? You know, that's not what I designed. And he was right. And we started to think about this. How can we avoid this second reflow, this second paint? And so how we solved that is after we've asynchronously loaded in the JavaScript, we can then cache it in local storage. So again, is it a modern browser? If it's not, just request with a link and be done with it. If so, is this a subsequent request? Do we already have CSS in the cache? Brilliant. If so, let's paint. And so now we have all of the styles to render the entire Guardian.com within the single HTTP request. If it's not, do we have local storage space? If so, let's request it in AJAX, push it into local storage, and then eject into the head. So the subsequent request rounds we've got. And here it is. And we also have to do a bit of caching validation here. So we use an MD5 hash of the CSS file and use that as the key inside local storage. So the next time round, we know what the latest key is. We loop over all of the objects inside local storage. If it's a new one, we nuke whatever is in local storage. So just a simple caching validation and inject the new styles for the next time. Really a massive gotcha that we had. Local storage, if you can't write to it, will actually throw a runtime error. And we learned that the hard way. So always wrap your storage rights in a try-catch. And then in the head of the document, as I said, on all subsequent requests, we check if it's there, instantly inject it in. All styles within the first HTTP request. And so when I've been talking to people about this technique, a lot of people ask us about how do we go about actually deeming what is the critical CSS. And Addy's actually going to do a great job at talking after me about how you can automate this process. But unfortunately, we try to automate it a lot. But with the sheer amount of modules and styles we have at The Guardian, we actually found that manually crafting these files is a lot easier. And it gives us a lot fine-grained control over an automated process that doesn't take into consideration JavaScript or adverts. So we have a set of 5 head files that we manually craft, benefiting from CSS preprocessors like Sass that we can just, this is our default one, we can only, and you'll notice here, as I mentioned, the critical content, just the article is the stuff that we're inlining into the page. And then we just have a simple IO string read and write, reads from the file, writes it into the server's response. So we've seen what that perception is to the user. What about the data behind this? So this is what our website loaded like before. I mean, it's a good shaped waterfall. That's what your most default website should look like. But we're blocking again on our start render event here. And so once we've inlined it, look at the location of that from before. So because we've declared this asynchronous, the browser's had all the information there, and it can start render instantly. It doesn't care about those other files. And so we've managed to shave 500 to 600, depending on the conditions of milliseconds, off our start render event. Most importantly, breaking our 1,000 millisecond budget, breaking the news to the user as soon as possible. So if you literally go open up your DevTools now, go to theguardian.com, you'll notice that there are no style sheets loaded into the page. And if you go and inspect your local storage, you'll see our CSS there, our global CSS file. And as Jed mentioned earlier, we also have taken this one step further and have started doing it with our fonts as well. And I really wanted to include this slide because it's my friend Tom that works at the Government Digital Service. And this Brad Wright, one of their other engineers there, said something that really, really rings home to me. And that all of this is just new forms of progression enhancement. But what a lot of people, when they've been talking about this technique recently, is that they focus on the perceived performance impact it gives. And yes, that's great. It does give users perceived performance impact. But more importantly, it makes you start to create resilient websites. Websites that are resilient to failure. Websites that don't care about the networking stack. And I can, if I'm on the train, I see a tweet, I could click on the link, and I go into a tunnel. Now, with a traditional website, I've made the initial HTTP request for the index file, but then I'm now in the tunnel, my browser's sitting there waiting on the network to download the CSS file. But on The Guardian, I can go into that tunnel, and my browser has all the information it needs. You're creating sites that are resilient to failure. Now, again, when I talk to people about this, a lot of people ask me, why don't we use cookies to do this? And so there's an interesting story behind this, that actually this technique isn't actually that of a new technique. And Steve Souders wrote a blog post way back in 2011, where he started to notice that the Google and Bing search pages were actually Google send down the entire styles for, even though I said that was a very bad practice earlier on, the entire styles for their page in the first HTTP request. But then they set a cookie, and then on subsequent requests, they check if that cookie's there, and then they don't send down any styles at all because they know that you've got them cached in local storage. So making extremely light pages, and Bing were doing exactly the same. So the reason why we don't do that is that we we've got quite strict edge caching rules so that we can cache everything on the CDN on the edge, that we try not to have any cookie logic at all. So we've opted not to use that, but I strongly advise you, if you do want to play with this technique, to use this. So you get the initial request, you inline the CSS, you can then render the page, go and fetch the rest of it, store it in local storage, and then drop a cookie. And then on all subsequent requests, you can check to see if that cookie's there, and then render a response with a default link, because it might be cache, or none at all, and then instantly render all of the information. Now, with all performance techniques, you must measure, optimize, and repeat. Okay? The foundation of every solid performance strategy is good measurement and instrumentation. And your websites will slow down, promise me. Ours does all the time. It's the nature of the internet. It's the nature of developing software. So you have to keep a monitor on this. And so one of the things I found the most annoying with using this technique is that this concept of what is critical content, what is the CSS that I need in critical heads. And so I found this problem a lot, that I'd go onto GitHub and I'd find one of my other colleagues including the new module in the default head file. It's just warning bells to me, like, hang on a second. And I then have to start a conversation on GitHub going, is this really a critical component? Is it above the fold? No, I don't think it is. What is it doing here? The minus, plus, thumbs down, bad. And so I started thinking to myself, how am I going to solve this problem? I'm getting fed up of having to start being mean to my colleagues. So I wrote a grunt task called Grunt Asset Monitor that we monitor every single, in our CI build, I'm monitoring all of the sizes of our JavaScript and CSS files, and so I can trend them over time. But more importantly, I can set thresholds for that 14 KB limit, and so I will get an email from my CI server telling me that some code that a developer's just checked in has just broken one of our performance budgets, and then I can go and poke them and say, can you sort this out, please? And so it's all well and good having real-time data like that, but we also need synthetic data as well for long-term trend analysis. So there's a lot of tools out there. We chose to use one called Speed Curve, and you'll see here, so I'm monitoring against all of even our own old site, our new site, and our competitors, the start render event here, and you can see that our trend, we're staying within our 1,000 millisecond budget. But the great thing about tools like this is that then they can get exposed to the business. We get an email every Monday morning that gets sent to the whole team, not just the engineers. So I can now start to instill this performance culture in our project managers, our designers as well. So when we have a change that's a breaking change, we might have not noticed it the week before, and my PM can now come and poke me and say, hey, what happened to the site last week? Why have we increased our load time by 10 seconds? You need to be able to instill that you can't just be you as a developer doing this. Performance is everyone's problem, and it's the designer's problem all the way up to your project managers, your stakeholders. Everyone must be involved and care about the speed of your site. Now, when I was planning this talk, Chrissy and Michael were like, yeah, but can you really involve some of the tooling? And fortunately, Addy came along to me last week and was like, hey, I'm going to do a whole section on tooling. And so I was like, yes, I don't have to do the tooling bit of it. And actually, is in much better hands than me, because Addy wrote most of these tools that are here. So he's going to go and talk about this later. But just, you don't have to do it manually. And if you just want to try it out on a new project today, there's a whole wide range of tools that are being developed around this. PageSpeed can do it on the fly for you. Addy's Critical, Basket.js, Scott's Load CSS, but as I say, Addy's going to cover all of that. Now, one thing that might be, I hope, is going through your mind right now is, but surely this is a hack. Why should we be having to trick the browser like this? This can't be right. It goes against all of our best practices, and I agree with you. And fortunately, there's a lot being done about it. So the first one is the Resource Priorities API. And so one thing about lazy loading your style sheets asynchronously at the bottom of the page is that browsers have a great feature called the look-ahead parser, the pre-parser. And what that does is it speculatively goes ahead whilst the DOM is being constructed and finds all the script tags and the link elements and actually starts performing the networking behind. And so by removing those style sheet link elements from the page, you're actually doing a detriment to the pre-parser because it can't find them. And so actually it is, again, a hack. But fortunately, the resource priorities has come up with a new attribute called lazy load that we can apply to videos, images, and in this case, for link elements. And just like async and defer on script tags, you're making a promise to the browser saying, I don't care about the CSS, actually. You know, it might be for an animation that's after a button's been clicked. And so you can perform the networking for it whenever you want. But most importantly, this is not a render blocking resource. You do not need to block rendering for this resource. And it wouldn't be any performance talk without mentioning HTTP 2. We're currently, all of us are using HTTP 1.1. That was finalized in 1997. It's shocking how we haven't had any change to underlying transfer protocol of the web for so long, but you know, it's actually such a good spec that we didn't need it. But now, this is in working draft. It's going to be finalized in November, and we can all start using it already today with protocols like Speedy. So what this allows in relation to this technique in CSS is that it allows multiple concurrent connections on the same on the same TCP connection. But more importantly, it has a feature called server push. And so in our traditional model, we're asking the server for the HTML file, we get it back, we then parse it, oh, right, there's a link element, go back to the server, get that, then we can render. With server push, us as developers know what the critical assets on our page are, so we can actually, when the UA asks the HTML file, it also says, hey, I know you're going to need a CSS file straight away after this, and this is my critical CSS file, so send it down at exactly the same time as the HTML file. So again, over the same TCP connection, we've already got all of the information. It does something quite clever that it just sends the header down because you might already have it in your HTTP cache. I can't wait to be able to use this feature. Finally, in this section, this is the web technology that I'm most excited about, and I think it is literally going to change the way that we create websites, and we think as developers of creating websites for good. If you're here for CSSconf, I highly recommend going to Jake's talk tomorrow morning about Service Worker, who's going to go into it in a lot more depth. But essentially what Service Worker is it's a separate worker process that runs in the background with your UI thread, and it's essentially a proxy layer that's intercepting every single network request for that domain. And you get past that request object in JavaScript, and you can decide whether or not how you want to respond to that. Either let it go off to the networking stack, or maybe pull it from a new cache object, which are incredible things. And so we've got our traditional request here, but actually, no, I don't want to go to the network. I've got this file in my cache. Return it instantly. And as I was saying, this will start to allow us to build resilient websites that don't care about their networking. And it's really going to change the way we develop websites. We must start thinking in an offline-first world. So before I go, I just wanted to summarize some of the key points that I tried to make here. And if it's anything you take away from today, please let it be these. Try to inline your critical CSS. And most importantly, defer all other non-critical assets. Nothing should be a render-blocking resource unless it is critical to your user. Where you can, cache aggressively, and always try to set a performance budget, but most importantly, measure, optimize, and repeat. I'd be really interested if some of you have been trying to set performance budgets as well, and please come and talk to me afterwards if you're trying out these techniques. We're developing the whole new site in the open on GitHub, so all of this code, all of these examples, and you can read a lot of the documentation and thinking we've got there. So we'd love people to help and contribute, and my slides will be up online there in about 5 minutes. Thank you.